Hello everybody and welcome to my 39th video. This is on quaternary counters and dividers. I'll be going through some of the circuits and design process for these counters or dividers. Yeah. So first of all, I have the unit operators which we're going to use. This is the unit operators from my video a quaternary post-algebra with counter maps, and these are the unit operators from our video a quaternary algebra with counter maps. So here we have A plus is A plus 1 modulo 4, A plus plus is A plus 2 modulo 4, A minus is A plus 3 modulo 4, A1 is a 1 A equals 0 and a 0 otherwise. Similarly, A2 is a 2 when A equals 0 and 0 otherwise. A3 is a 3 as A equals 0 and 0 otherwise. So here we have A. This is A bar. This reverses the order of the truth table. So in response to 0, 1, 2, 3, you get 3, 2, 1, 0. And this is Z. This is 3 times A. I'll be using that here, which I'll explain in a bit. These are the unit operators for the other algebra. For example, A00 is a 0 is a 3 when A equals a 0 and 0 otherwise. For an example, A11 is a 3 when A equals 1 and 0 otherwise, etc. These are other unit operators for the algebra. Right, so we'll go on to the flip-flop symbols. This is a D-type flip-flop with a D input, Q and Q bar outputs. This is Q bar. If this is Q, this is Q bar. 3, 2, 1 in response to 0, 1, 2, 3. Set and reset. Set and reset are active low, so quaternary logic 0 activates the reset or the set. Otherwise, it's tied to a logic 3. Quaternary logic 3. T-type flip-flop, T input, Q and Q bar again, set and reset. JK flip-flop, J and K inputs, set and reset, Q and not Q. All these clocks here are negative edge triggered from a quaternary logic 1 to a quaternary logic 0. So here you can make a D flip-flop from a JK flip-flop by adding this gate in here. This is not X, this is this operator here, and the T-type flip-flop you introduce the Z function to K. Z is here, which is 3 times A modulo 4. Here I'm going to go through the quaternary JK excitation table. So we'll be using this in some of the designs using JK flip-flops. So here we have Q and Q plus. This is the present state, this is the next state. Q plus is the value of Q after the flip-flop has been clocked. So here we have the axis can assume any value 0, 1, 2 or 3. And for here, for these group 4, when Q equals 1, whatever value you choose for X, for J, K is equal to 2 times J plus 3. So for example, if X was 0, 2 times 0 plus 3 is 3, so K would equal 3. Similarly, for Q equals 2, we have this arrangement here. X can assume any value 0, 1, 2 or 3. Whatever value you choose, J is equal to 2K plus 3. For example, in this example, this line here. So for example, if K was 1, 2 times 1 plus 3 is 5, which is 1 modulo 4. So J would be 1. Similarly, for Q equals 3, we have this setup. X can assume any value 0, 1, 2 or 3, and K equals 3, 2, 1, 0 in response to Q plus 0, 1, 2, 3. So that's the quaternary JK excitation table. Here we have a divide by 2 circuit. So this is the table for this circuit A here. Here we have the Q and Q plus present state and next state, and the values of J and K I've just written in as the table, as in the previous table. So J equals a 3, X can be any value, 0, 1, 2 or 3, so I've let it equal a 3. Here J is a 0, so I've let K equals 2 times 0 plus 3, which is 3. Here X is a 3 for K, so 2 times 3 is 6, plus 2 is 8, which is 0 modulo 4. So J is a 0, and I've used X equals 0 there and kept the 3 there. That just means you don't have to provide a startup reset for a divide by 2. But here in circuit B and circuit C, you do have to provide a reset. So in circuit B uses a D flip-flop and ties D to Q bar, and JK flip-flop, both J and K are equal to 3. So here's the timing diagram. The clock alternates between a 0 and a 3, providing a negative edge for the clock between a quaternary logic 1 and 0. And so every 2 clock pulses you get a change of 1 clock pulse from Q, the output Q. And I've provided a momentary reset here, so it resets Q to 0. Right, that's a divide by 2. Here's a divide by 3 circuit. There's only one circuit to do it. We're using a JK flip-flop. Here, a 0 goes to a 1 goes to a 2, and a 2 goes to a 0, providing three counts. So I've arranged a 3 here to go to a 2, then for a 2 goes to a 0, and then 0 goes to 1, 2, and 2, 0 again. So that just means you don't have to provide a reset. It automatically goes into the count if Q should start up as a 3. So here, this is the JK excitation table as before. So here I've chose X equals a 1. Here I've chose X equals 0. So K equals 2 times 0 plus 1, which is 1. Here I've used K equals 1. So 2 times 1 plus 2 is 4, which is 0 modulo 4. And here I've used X equals 0, and then 1, K equals 1. So here we have the circuit diagram with the X1 unary operator from the Q to the J and K set to 1. K is 1 there, and that's the output from X1. So the timing diagram, clock 0 cycles between 0 and 3, Q cycles 0, 1, 2, and then back to 0 again to continue 0, 1, 2, and back to 0. This is a startup reset. You don't technically need it, but I've just put it in there to set Q to a 0. Right, so that's the divide by 3. So a divide by 4 circuit. Here, the 0, Q, this is Q and Q plus, present state and next state. 0 to 1, 1 to 2, 2 to 3, 3 to 0, cycling. Here, X is a 3 and J is a 1. Here, X equals a 1, and 2 times 1 plus 1 is 3, so K is a 3. Here, K is a 3, so 2 times 1 plus 3 is 5, which is 1 modulo 4, so J is a 1. And here I've used J equals 1 for that X there, and kept the 3 there. So this applies to circuit A for this table. J is a 1 and K is a 3. And for a T flip-flop, implementing it with a T flip-flop, T is tied to a 1 constantly, and for a D flip-flop, use a quaternary successor gate from the Q output to the D input. Right, so this is the clock time diagram. The clock cycles between 0 and 3. Q goes 0, then 1, then 2, and 3, and back to 0 again, and cycles. And this is a startup reset, which resets Q to 0. Right, this is a 3-column ring counter. Circuit diagram here, table there, truth table there. All I could find out about a quaternary digit is it's sometimes called a crumb. So hence the name 3-column ring counter. So here we have the setup, which sets QA to a 3 and resets QB and QC to 0, which is this state here. Then you apply the clock, which is wired synchronously, they're all wired together, and it cycles between 3 cycles round from QA to QB to QC. The feedback, this is the feedback which is shown here, and that goes to the D input of QA. So it just cycles between these QA, QB and QC. Right. This is a 3-column twisted ring counter. The same circuit as before, except it's got a successor function in the feedback loop between QC and the D input of QA. So basically, it's a similar circuit as before, like I said, but the feedback adds 1 to QC. So if it's a 0 there, it's a 1 there, a 1, a 2, 2, 3, 3, 0, and the feedback enters QA there, and the decode, well, the purpose of the decode is to give a logic 3 on one line only and a 0 everywhere else. So for example, QA and QC here are 0 and 0 there. So that's the maximum of function, the plus. And that gives us 0 for 0, or 0 max 0 equals 0. Then the x3 function gives a 3 if the term in the bracket is 0, and a 3 and a 0 otherwise. So that gives a 3 for this line only, because QA and QC are zeros only on this line. Similarly for this line here, QA is a 1 and QB is a 0. So QA minus would be a 0 when QA is a 1. So that would be a 0 at this line here, and that would make it a 3 on the output of the x3 function. So it's a 3 on this line only and a 0 everywhere else. Right. So here, same circuit, reset all the flip-flops to make it 0, and then common clock for synchronous clock. Right, well, here we're going to have a synchronous modular 16-up counter. I'm going to implement this with T flip-flops. Right, so here we have QA and QB, which is the present state, QA plus and QB plus, which is the next state, and this is input TA and TB corresponding to a QA and QB. So QA counts up all the time, so TA is permanently set to 1, so if T is a 1, Q plus is Q plus 1, and TB only increments, QB only increments on a transition of QA from a 3 to a 0, so TB is a 1 when QA equals a 3. So if this is QA, this is not QA, and this is QA, not QA1. So QA, not QA1 is a 1 when not Q is a 0 and a 0 otherwise. So that gives you the one at QA equals 3, which is what you see here. Here and here and here. So TA equals a 1 and TB equals not QA1. Here we have the timing diagram, the clock cycles between 0 and 3, and QA goes 0, 1, 2, 3, and cycles 4 times, and QB goes 4 zeros, then 4 ones, then 4 twos, and 4 threes, and the cycle repeats. And TB is a 1, this is TB here, when QA equals a 3, so not QA would be a 0, so that the input is to the X1 gate is taken off the not Q and feeds into TB, which is here. And I've included a reset there, which is here. Right, so that's synchronous modular 16 up counter. This is a synchronous modular 16 down counter. Here QA, QB, present state, QA plus, QB plus, next state. QA, I'm using T flip-flops again, so we've got TA and TB. QA constantly counts down, so TA is set to a 3, T is a 3, Q plus equals Q plus 3, which effectively counts down. And QB changes from QA equals 0 to a 3, so TB is a 3 when QA equals 0, 3, 0, 3, 0, 3, 0. I've shown that here. This is Q. Q3 is a 3 when Q equals 0, QA equals 0, and 0 otherwise. So TA equals 3 and TB equals QA3. Right. So this is the circuit diagram, timing diagram. Clock cycles between 0 and 3. QA and QB. QA cycles from 3 to 1 to 0 and repeats 4 times. And QB provides 4 logic 3s and 4 logic 2s and 4 logic 1s and 4 logic 0s. And then the cycle repeats. And TB is a 3 when QA equals a 0, which is shown here. And I've shown this is a set function which provides a momentary set to set QA and QB to 3. So this is the set here. Not R of QA and QB are set to 3s here. This is a common clock, and X3 is off QA, feeding T2. Right. So that's the synchronous modular 16 down counter. Here we have an asynchronous modular 10 up counter. Basically QA and QB count up from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then on the 10th one, the clear, which is this reset circuit here, clears the circuit, clears the QA and QB to 0, resets it. So, of the circuit diagram, QA feeds the clock for the next stage. The T inputs are set to 1 permanently, and when QA is a 2 and QB is a 2, X22 and B22 are 3s, which gives a 3 on the minimum function, but the minimum function is negated So when it wouldn't give a 3, it gives a 0, and that gives you the 0 there, and it resets the flip-flop to 0, 0 here. So that's the asynchronous modular 10-up counter. Here we have the synchronous modular 64 counter. I've just provided the circuit diagram. Basically, the clock from the Q output feeds the clock to the next stage all the way through. Counts up the outputs are taken off the Q, and this is the most significant digit and the least significant digit, and not Q. Count down the outputs are taken off the not Q. This is the least significant digit and the most significant digit. There's a common reset. Synchronous modular 64 counter. All the clocks are connected together, so it's synchronous. The reset there, and basically when Q equals a 3 on this, not QA is, well, Q bar A is a 0. That provides a 1 there, which counts up on the clock. And here, T is a 1 there when QA and QB, for example, are 3s, so these would be 0s. So the 0 goes into the max function, which gives a 0 output, and the x1 gives a 1 when the output from the max function is a 0 and a 0 otherwise. So basically you can have another stage with a max function and an x1 function with the outputs fed from not QA, not QB and not QC, for example, for a next stage. Right, well, that's that. Now I'm going to go through a synchronous modular 13-up counter. We have QA, QB, present state, QA, QB plus, QA plus, next state. I'm going to implement it with the JK flip-flop. So I've listed the excitation table for the JK flip-flops here. QA and Q plus have inputs J and KA. QB and QB plus have inputs JB and KB. So I've filled in the excitation table here, and what I've done is I've worked the J's and the K's out in this column here. I've kept the X's where it's appropriate to find an X, and I've made the KA, J, KB and JB 2-valued, as you know, because that simplifies the logic and the counter maps, the logic design. So for example, from QA equals 2 to the 3, J equals 2K plus 3, and K equals X. So I've chose X equals 3 here, so X equals 3, then 2 times 3 is 6 plus 3 is 9, which is 1 modular 4. So that's there. Get the X's for that one. KB, yeah, there. For example, that's QB. Let's have an example here. QB equals 2 to a 3. X I've chose to be a 3, and on the same thing, JB equals 2 times 3 plus 3, which is 9, which is 1 modular 4. So that's how I produced the logic tables for K, J, KB and JB. Here are the counter maps. This is J and K. So QB here, I've chosen QB 0, 2, which would normally give a 3 for cube equals 0, 1, 2 and 3, but I've minimized it. Well, I've put a logic 1 and used a minimum function to tie one input to a logic 1 and then the other input to QB. So J equals 1 min 0 QB2 to give a 1 instead of a 3. Here for KA, I've kept all the inputs to be a 3. X is a 3 here. And here, this X is a 0. For JB, I've done the same trick. It would be a 3 normally. 3 QA3 would be a 3 for that line there, but I've tied one input of the minimum gate to a 1 and fed the other input into QA33. So that makes it a 1. So JB is 1 min QA33. And for KB, this is QA33, this is QB33. So these X's are zeros, and KB equals QA33 max QB33. This is the circuit diagram for the counter, modulo 13 counter. Here we have JA, the minimum function in X02. This is KA is a 3 permanently. JB follows QA33 tied with a minimum function with one input tied to a 1 and the gate from the other input to the other input, and then that feeds into JA, and this is the maximum function, which is QB33 and QA33, and that feeds into KB. Right, so that is the circuit diagram for the counter. Lastly, I'll have a startup reset counter circuit. Basically, when you apply the supply voltage, this capacitor here charges through this resistor and is the output is momentarily quaternary logic 0. Then when the voltage on the input reaches threshold voltage, it goes to a quaternary logic 3. And this diode here is so if you accidentally switch off the power, it discharges the capacitor through this diode here to earth. So it provides, if you lose power, it still provides a reset. So this is a set, a reset, or a setup in the circuit diagrams for the counters and dividers. Right, I think that concludes the video. Just like to say thanks for watching. Hope you've enjoyed it. Bye.